Welcome to today's webinar. The topic today is buckling analysis in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the Dlubal website, the German and English webinars, newsletters, customer projects, and so on. I will be the moderator today, and I will also be a presenter, at least of the first part of the webinar. And we all together answer your questions. I say some words with the next slide, how you can ask questions for the attendees who participate the first time. But before that, my two colleagues can introduce themselves. Jonas?
Yeah, hi, welcome also from my side. My name is Jonas Bien and I'm working at Dlubal for a year now, something like this. And I'm focusing on the development in the steel design, context of steel design and structural stability. And I will present the second half of today's webinar, and aside will answer your questions. Yeah.
Okay, so hello and welcome to the webinar. My name is Oliver Metzkes. Here at Dlubal, I'm working in the customer support and also as product engineer, mainly also responsible for the steel design add-on. And today I will answer your questions during the webinar.
Okay, thank you for your introduction. Then we can switch off our webcams that the attendees can see the full screen. You can see the control panel on the right side of your screen. You can show that with that arrow here, and then you can enter a question here. And we will answer you. In the case you don't get an answer during the webinar because there are too many or you are too late with your question, then you will get an email after the webinar. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, to the agenda today. As already said, I present the first part of the webinar, an analysis for shell buckling using the global M&A and LBA calculations. On an example from a seminar paper from Professor Schmidt. You will see that with one of the next slides. Then I take over to my colleague Jonas Bien, and he will do an analysis for plate buckling using the GMNEA method according to Eurocode 3 part 1.5. Okay, at first, a short overview about buckling analysis of shells. There are different possibilities. First possibility is the stress-based buckling analysis. A simple application, often done by hand calculations. But it's quite difficult to achieve economic results. So the second possibility is the design by global numerical M&A and LBA analysis. That's what we do today. In the next example, there's more background knowledge necessary. The computer should be able to do an M&A or LBA and an LBA analysis. RFEM can do that, and we will do that with the program. Okay, and the third possibility is the design by global numerical GMNIA analysis, where there's excellent background knowledge necessary. You must apply the imperfections correctly. And the computer technology, there are considerable requirements. It's no problem for RFEM 6, of course. Okay, then we turn to the example. You can see that cylindrical silo with different wall thicknesses The material is S235. And it's filled with a liquid so that you have there's applied pressure from the liquid and a pressure, earth pressure from the outside. And we apply the load difference, 8 kilonewton per square meter in that area, and in triangular load in that area. Only the load difference as design load. Okay. Yeah, and we enter in RFEM only the silo was, including that boundary conditions for shells according to Unicode 3, part 1.6, and of course the load. Okay, then I turn to RFEM. I've already prepared the lower ring, that we save a little time, but I would like to show you some features for the attendees who don't already work with RFEM 6. That's the steel shell. You can see the thickness is 10 millimeters. It's 3.5 meters high. I can copy that by selecting it, then press the Control key, and you can see the plus. That's the sign that I copy the shell, and then I move it via drag and drop to that point. So, because that ring is also 3.5 meters high, according to our example. Then I need to select both surfaces. Then I double click on it, and I need to modify the thickness. I create a new thickness of 8 millimeters. Okay. Same material. Okay. And you can see in the panel that the thickness of 8 millimeter for the middle ring is created. So, and the upper ring is 3 meters high. That's why I select only that ring line. So, and then right above, I go to Move Copy Selected Objects. I create a copy of the lines. One copy, -3 meters in Z direction. Then I select under numbering and options the step links, and I check link lines with surface. And I need to create such a surface. Okay. The material should be S235, but we have to create a new thickness, 6 millimeters. Okay, now you can see the different colors also in the panel. Okay, I need to define the line supports on the upper side. Here left above, assign line support. And I create a new one. Not in Z direction. We use the local coordinate system. We would like to support it in X or local X and local Y direction, in ring direction and perpendicular to it. Okay, that's all. The model is finished. We still need to apply the load. And that's a new feature in RFEM 6. You can apply varying load of all surfaces with one step. So above, new surface load. I select all the surfaces. Okay. Then load distribution. varying in Z, the global Z direction, you can define different values over the height. So I switch to the local coordinate system for the surface, and we would like to apply the load perpendicular to the surface area in Z direction, local Z direction. So we only need to define the parameters. We start with the upper value, -10. It's 0. Then in -9.2, where's the value -8. And at the bottom, we have also the value -8. That's all. And you can see the load as in our example. Maybe we can compare it. That's the load. And we have also created or defined different thicknesses. So I turn back to RFEM. Then we define here above the mesh size, mesh setting, and we use 25 millimeters for this example. Okay. So in the next step, we go to the load case. It's still named self-weight. I call it design loads. As in the example, I don't activate the self-weight, that I get the same results as in the example from Professor Schmidt. So, and I do a stability analysis. This is only activated if you activated the structure stability add-on in the base data. I show you where you can find it. That's when that's the base data. When you create the new file, or you can turn back to that dialog with that button right above. So, and under add-ons, I've already activated the structure stability add-on. And for the M&A analysis that we do in the next step, the nonlinear material behavior add-on. And I switched off the combination wizards and load wizards. Okay, then we can run the calculation. And we are waiting for the eigenvalues. That's the statical analysis and that's the stability analysis. 2 steps. We have to wait some seconds. So, and now we take a look in the table, not in static analysis, but in stability analysis, and we can see our eigenvalues. So we calculated only the lowest 4 eigenvalues. When you click on it, you can see the different mode shapes. They are quite similar. And we turn over or take over the lowest critical load factor, 1.504 in our example. I turn back to the PowerPoint slide. And that's what we have just calculated. The elastic critical buckling resistance ratio. We need it for our analytical formulas that are in the next slides. Okay, then in the next step, we calculate the plastic reference resistance ratio. If it is not possible to do an M&A calculation, it's allowed to derive the plastic reference resistance from a linear shell analysis. And you have to take this equation here from the standard. That's a little bit complicated, but we don't need to do it. we calculate this value with RFEM 6. Maybe in additional information, you can download the PowerPoint slides, the complete PowerPoint slides from our website. At the end of the webinar, I show you where you can find these, this PowerPoint, or we offer it as a PDF file. And you can also download in the next days the recording. Okay, so then we change the material. I double click on it, and it's steel S235, and we switch it from isotropic linear elastic to isotropic plastic for surfaces and solids. So that's the model. I think you know that graphic for steel, the elastic path and the plastic path. Okay, so, and what we also need to do is to change the stability analysis settings. I double click on it as well in the navigator data. And we switch to the incremental method without eigenvalue analysis, nonlinear. And we would like to increase the loading. Now we start with the initial load factor 1. The load factor increment can be 0.1 as the default setting is. Then the refinement for the last load increment, 10. But we switch or change the maximum number of load increments to 1000. And I activate when the program should be stopped the load increasing if the deformation is higher than 300 millimeters. Then the program should stop the increasing of the load. Because when you have got deformation over 300 millimeters, then the structure collapses. We would like to save the results of our load increments, and then we can leave the dialog. If we now run the calculation, the program would, or the calculation would take maybe 4 or 5 minutes. We skip the calculation time. I switch to an already calculated model. So, and then we need to turn to the table, incremental stability analysis. So I increase the table a little bit, and we can scroll down, and that's the critical load factor 35.6 that we use for our equations. You can also, we save the calculation diagrams. We can double click on it. So, and then you need to select the incremental stability analysis. Then the result type should be the load factor for the horizontal axis, and for the vertical axis, we would like to use the maximum deformation. So I increase the window. And you can find the value 35.6 in that 3 here. Then that should be the point where the structure collapses. You can also print that graphic or that diagram directly to the printer or to the printout report and so on, just for your information. So let's overtake this value, 35.6, in the PowerPoint. So that's the value that we calculated. And then we set in the values in the formulas or equations from the standard. I mentioned the equations from the standard here, and you can find also the standard Eurocode 3 part 1.6 in the bibliography of the PowerPoint slide. So we calculate the overall relative slenderness. That's the value lambda of V, 4.87. Those are the circumferential elastic imperfection reduction factor according to table D5. Then the plastic range factor according to D26. Then we calculate the plastic limit relative slenderness according to equation 8.16. And this comparison shows that we have got pure elastic buckling. That's the buckling reduction factor according to equation 8.15. So and that's the last slide. We calculate the characteristic buckling resistance ratio 1.125, and then the design buckling resistance ratio according to equation 8.27. And we can see that the design is fulfilled. Okay, that's a link to another example on our website. Now, as I mentioned, you can download the PowerPoint slide and click on that link, for example. So that's all to the first example, and I hand over the screen to my colleague Jonas Beam. Just a moment.
Yeah, thank you, Andreas. I will agree to share, of course. That's what I'm here for. Yeah. All right, then another welcome from my side. I would now go on with the second example. So after Andreas has now nicely demonstrated how to set up an MNA, so materially nonlinear analysis, or an LBA, linear bifurcation analysis with RFEM, to assist the verification process of buckling-prone shells, I would like to further increase the complexity a bit and show you how you can also perform GMNEA analysis with RFEM 6 in the context of plate buckling. For that purpose, I will adopt an old example problem that was discussed in a webinar with the identical topic of this one just about 2 years ago. So we have a 14 millimeter plate that is supported on all sides. It's loaded in longitudinal compression and shear, and we have a centric trapezoidal stiffener. Back then, Andreas, who is now already also presented the first part of the webinar, used our tool FE buckling to do the verification check. And that means that after this webinar, you have the chance to compare the modeling and verification procedures of both analysis types, so with FE buckling and now with the GMNEA in RFEM 6. But because the GMNEA is quite complex analysis concept, I would like to share some fundamentals before I go to the program. So first of all, what are those abbreviations standing for? What are all these letters that we are throwing at you? So GMNEA stands for geometrically and materially nonlinear analysis with imperfections and is the most complex static analysis type. As the name already suggests, large deformation theory is required and a material nonlinear or nonlinear material model needs to be also established. Moreover, an imperfect geometry is used for the analysis to account for bulbs that are already in the geometry or residual stresses that come from the manufacturing process. The aim of such complex analysis is to take all the aspects that significantly influence the structural response explicitly into account on the modeling side, and thus reduce the number or the dependence on simplified semi-empirical verification procedures that sometimes lead to unreasonable or uneconomic results, or this is also frequently the case, are not even available for your problem that you want to solve. However, in addition to a powerful software, such as ours, of course, sufficient experience is required on the user side. So this is also explicitly written in the code. Where it stands, I will shortly show. Because in fact, the quality and robustness of the results strongly depends on the modeling and solution settings. So this is why I want to show what I want to focus on the most critical parts of a GMNEA. Okay, so hints and rules for the buckling verification by GMNEA are given in Annex C of Eurocode 3, Part 1.5. This will probably change in the near future in the new generation of EC3. All topics related to FE analysis will move to a dedicated part 114, with the name Design Assisted by FEA. But as far as I've seen, it seems like for the most parts, the rules that are currently valid and written in Annex C of Part 1.5 will still remain valid in the next generation. Besides that, for additional tips, benchmarks, and examples, I can also recommend a handbook from ECCS with the name of Design of Steel-Plated Structures with Finite Elements. Has just been published this year, and I added the reference to the bibliography in the last slide of this PowerPoint. All right, last slide before we go to the model. So a GMNEA resembles a virtual load bearing test of the examined component. We try to increase the external load until a clear failure state of the structure or the component is reached. For the determination of the critical load factor, two limit states are defined in section C8 of Eurocode 3 Part 1.5. The first one is the load factor when the maximum of the load deformation curve is reached, and the second one, the load factor when a certain limit strain or deformation is reached. In the main standard, a limit of 5% principal membrane strain in tension is recommended as a limit criterion. The minimum of both of those load factors is then compared with the product of two safety factors that's written below here, and those safety factors take into account the uncertainty of the numerical model and the uncertainty of the load and resistance models. All right, so I think that's enough said. I now want to show you how we can perform such analysis in RFEM, and therefore I directly jump into the program. I have already prepared the basic model for this webinar, so we don't waste too much time. So we have the 40mm plate with a centric trapezoidal stiffener. The plate thickness of the trapezoidal stiffener is 6mm. The material for all parts is mild steel S355. But let's check what material it actually is, and we can see that until now I have only applied linear elastic material model here. So I will change that in a bit after showing you the rest of the features of the model. So the stiffened plate is supported at all four edges by line supports in Z direction. And then to stabilize it or to avoid rigid movement in the XY global plane, I added two nodal supports here in the corners without over constraining the model. The dimensions I've added two, 5 meter length, 1.75 m is the width of the total panel, and the width of the sub panel, that is, this whole panel can be divided into 2 sub panels by the stiffener. So the width of the sub panel would be 0.725 meter. Okay, let's quickly hide the dimensions, because otherwise they will just be a bit confusing. And lastly, I want to show you the loads. In the original slide I showed you, we had stresses that were applied to the boundaries of the plate, but we can't define stresses on lines in RFEM 6, so we have to calculate line loads. So this is quite straightforward. If we want to have stress at this edge of 21 kilonewton per centimeter square, we just multiply it by the plate thickness to get a line load of 29.4 kilonewton per centimeter. And we do the same for the shear load, which you can see hopefully here, which is 1 kilonewton per centimeter square times 1.4 centimeters thickness of the slab would be 1.4 kilonewton per centimeter. Maybe one short note to the load application. We have to keep in mind later, if we perform the GMNEA with a non-linear geometric theory, it matters if the load is defined in the global coordinate system or the local coordinate system. So if we define the load in the global coordinate system, the load will stay true in the defined direction. So it will be applied in X direction no matter how the line is deforming along the analysis. If we would apply the load to the local coordinate system of the line, the orientation of the load would move with the line throughout the analysis. So that's one important part to keep in mind when defining loads for analysis with nonlinear geometry. All right, then let's tackle the first nonlinearity, which is the material nonlinearity. In order to be able to choose nonlinear material properties, I need to switch on the add-on nonlinear material behavior. And I, in this step, already also activate the structure stability, because we will need the linear bifurcation analysis and then later on also the incremental analysis that Andreas already used in his example. So I switch them on, say OK. And now if we double click on the material and look under material models, we will have also nonlinear material models available. And for our to model the real behavior of mild steel, we would go for the isotropic plastic material. I have to take the surfaces on solid model. It is split from the member model, so we have to make sure that we select the right one. So then the question is, we have multiple options for the yield, which yield hypothesis we want to apply, and also how the stress strain diagram should look like. And in order to choose a suitable one, we can look under section C6 of Eurocode 3 part 1.5. And the Eurocode gives different material models that can be used. So it always recommends to use the von Mises yield criterion, but we can use different material models for the GMNEA. Basically, we can neglect hardening of the material on the safe side. We can also only account for pseudo hardening as shown here in the material model B. This is just very small linear hardening just to increase or improve the convergence behavior of the numerical simulation, but without having a significant impact on the analysis results. But the Eurocode also allows to take the hardening into account. So we could use a bilinear model with a linear hardening of E divided by 100, for example, or similar value, or if we are certain about the material properties of the steel we use, we could also put in our true stress strain curve. So, but in our example, we will stick with a linear elastic, perfectly plastic material model with pseudo hardening. This is basically the standard setting for the plastic isotropic material model. So in this case, it's E divided by 100,000, but this is still okay. So we choose the basic material model that we have as default setting in RFEM 6. Okay, now that is already done. Then the second part would be to think about the imperfections. So which imperfections do we need to apply and how should they look like? So also on this question, we find answers in the Eurocode 3 part 1.5. Under section C5, there are, I think, 4 or 5 different types of imperfections. For our example, these are the 2 that are relevant. So we have a global imperfection of the whole panel, including the longitudinal stiffeners, and the imperfection shape should be a bow shape with the magnitude of the minimum plate dimensions divided by 400. Then we also have a local imperfection type for a sub-panel. Here, buckling shape should be affine to, or the shape of the imperfection should be affine to the buckling shape with the magnitude of the minimum of the sub-panel dimensions, A and B, divided by 200. Although for the global imperfection, it says a bow type imperfection should be used, it's quite common to use a buckling shape affine imperfection for the global imperfection type as well, as long as the buckling shape or a buckling shape can be found that is affine to this bow shape. One thing I'd like to add here, so the imperfections that are mentioned here are equivalent geometric imperfections, and they include both imperfection types, geometric imperfections and structural imperfections that result, for example, from residual stresses due to fabrication. So if we look into our model and think about welding this trapezoidal stiffener to our plate, then of course, due to the welding and non-symmetric heating of the plate, we will probably get some residual stresses in the plate. All right, so how do we apply those imperfection or affine eigenshape affine imperfections in RFEM 6? Therefore, we need first to set up the linear bifurcation analysis to find the eigenshapes. We do this. I already activated the structural stability add-on, and by doing so, I have this option to calculate the critical load with our stability add-on for our load case 1. And I will change the default settings a bit because I'm usually interested in much more eigenvalues. So I will, in this example, I'm interested in the first 20 eigenvalues, so I will increase the number of eigenvalues that shall be calculated. And by doing so, that should already be set up for the linear bifurcation analysis, but I forgot to mention one thing, and that's the meshing, the discretization of our problem. So how should our mesh size look like? When I generate the default mesh and use the default mesh settings, we see that it's way too coarse. So we have one element over the sub-panel width and so on. So that would not be suitable for our simulation. So it is hard to get or to give general recommendations about the mesh size because it depends on the model, on the loading, on the type of investigation, on the results that you are interested in, and so on. But a good rule of thumb for a linear bifurcation analysis would be that you should use at least 6 to 8 linear shell elements over one buckle. So if you expect one buckling half shape within this over the width of the subpanel here, we should at least use 6 elements over the width of the subpanel here. So I will refine the mesh a bit from 50 centimeters, which is the default setting. This is probably good enough for concrete slabs or base plates in some cases, but for a GMNEA of such component, it is always never suitable. So another general rule of thumb is, of course, the mesh should be as fine as required for the job, but as coarse as possible to save computational time. And in doubt, so if you are not sure if your mesh size is sufficient, you should of course also do a mesh convergency study so you should refine your mesh step by step and see how the results change and how it affects your final results. I have done this. I can show you the results later on. Yeah, but it's always a good idea if you are unsure. All right, so now with a decent mesh size, I can start the linear analysis and the linear bifurcation analysis. So these are the 2 steps that are now selected for calculation: static analysis and stability analysis. So this is always, if you do that for the first time for your model, it's always a crucial step, because when it runs, then you know that all parts are connected, and you can check by analyzing the static analysis results how the structure behaves and so on, if the supports are set correctly. So what we see here, by applying the load only to the plate, we see that this is of course some eccentricity to the overall section of the stiffened plate, so it bends upwards. And what's also interesting, or I could show you how is the stress state in the static analysis. So what are the maximum stresses? The maximum von Mises stresses in our model due to the design loads are at 235 megapascals. So they are way below our yield stress of 355. So in an elastic design, that would look totally fine. That wouldn't worry us. But what about the stability? We can check the stability results by going to this solution type. We can do that via this drop-down menu here in the navigator or in the table, and then browse through our eigenshapes. And what we see here, the first eigenshapes, they are all buckling of the subpanels. So the overall panel is divided by the stiffener. The stiffener provides enough stiffness to do that to the buckling prone plate. And of course, the wavelength changes from one mode shape to the other. And okay, this is interesting. Mode shape number 19 would be the first global mode shape where the whole plate, including the stiffener, buckles. So that we should keep in mind. Of course, the critical load factors are also interesting. So we have a factor above 1, but below 15 or 10. So we should worry definitely about buckling instability. So yeah, it's good to do further analysis on this. All right, we can now adopt. So now we have performed the linear analysis and the linear buckling analysis, and we want to now apply eigen-shape-affine imperfections for the GMNEA. To do so, we go to imperfections and create a new imperfection case of the type buckling mode. This is only available if you have the structure stability add-on activated. And I want to select a load case as my source for the buckling mode. yeah, and I have only my load case 1, where I performed my LBA analysis, so where I have some buckling modes calculated that I can use to scale them for the GMNEA. The question, of course, is, okay, which buckling mode is the most severe? Basically, you should apply the imperfection that leads to the lowest load factor in the GMNEA analysis, but of course, that's not always clear. So it may be, I think it would be a good starting point to start with a mode shape that has the lowest critical load factor, but it's not guaranteed that this is the most critical imperfection for your GMNEA analysis. So also here in doubt, we need to take several mode shapes into account and do a GMNEA with all of them. For this demonstration, I will just check the first local mode, that was buckling mode number 1, and the first global mode, which was buckling mode number 19. Then we have to also take into consideration the scaling direction. I want to scale it spatially, so as it comes out of the stability analysis. And the magnitude, I can again show you the slide from the Eurocode. So for the local imperfection, it would be the minimum sub-panel dimension divided by 200. I can enter this as a formula condition. So I would enter here minimum of 0.725 meters and 5 meters, which would be the length of the sub-panel, divided by 200. And then click apply. Then the question is, okay, should it be directed upwards or downwards, or should the scaling direction be in positive or negative direction? That depends pretty much on the mode shape itself. So if we study this first mode shape that we just used for the eigenshape affine imperfection, we see that the mode shape is asymmetric about the center line in X direction of our panel. So that would mean that anyway, if we define it in positive or negative direction, we would have one side of the plate where the buckle is oriented upwards, and on the other side it would be oriented downwards. So it shouldn't matter for this mode shape in which direction we define the pre-imperfection. For other mode shapes, such as the second one, of course, it could matter because this mode shape is symmetric, and it could give different results if we apply the imperfection in the direction shown here or in the opposite direction. So also here in doubt, we need to apply or check both directions. But now back to the imperfection cases. I can very easily apply those imperfection cases. I can just copy this. To not confuse you too much, I will name them mode shape 1, which is a local one in positive direction. And then the second mode shape I want to check would be the buckling mode 19. I apply this also in positive scaling direction. Mode 19, it's a global one. And now we have to take care of the imperfection magnitude, because here the dimensions of the global panel are to be used, and it's not 1/200th, but 1/400th of this dimensions. All right, and yeah, because this buckling mode is symmetric also, just as I've shown you for buckling shape number 2, I will put them or apply them in both scaling directions, just to check which one is the most critical one. Then also, according to Eurocode 3.1.5 or part 1.5, we need to take into account the interaction of both imperfection types. So in RFEM, we have the possibility to create groups of imperfection cases. So I could I could combine imperfection case number 1 with the local imperfection case with the global imperfection case. Therefore, I have to set an operator here and a scale factor. So according to Eurocode, we can apply one as a leading imperfection with 100%, and the other one would be or could be applied with 70%, but on the safe side, and to not create too many different groups, I just apply them both with 100%. That's a safe side assumption, so I can go with this. And that would be imperfection case 1 plus imperfection case 2. And because I'm not sure if this combination or the combination of mode 1 and imperfection case 1 and imperfection case 3 would be the most crucial one, I also take into account another group where I add up imperfection case 1 and 3. All right, so now we have defined all of our imperfection cases, so we can set up our GMNEA. For that, I could copy my load case 1 and apply different analysis settings to it, or I could use or abuse our combination wizard to automatically generate load combinations with all imperfections based on our load case 1 here. And I will just show you how to do that, because that's very convenient. And if I add imperfection cases, I don't need to manually add load cases. So I just delete all the preset design situations and add an accidental design situation, because in this design situation, all load cases are combined with a factor of 1.0. So that's quite nice. And then I changed the combination wizard to tell him which settings to apply for the load combinations that are generated. So for our GMNEA, I want to do a large deformation analysis. So for that, it would be most appropriate to take also the large deformations analysis settings. So this is suitable for large deformations and large rotations. The second order theory is maybe not always suitable. So in doubt, I would always take the large deformation theory. And then in order to do to get this characteristic of a load bearing test, which we want to do virtually, I also consider the incremental analysis, a stability analysis. So I just add this new type here that already Andreas already introduced you to this type of stability analysis. And I will start with a load factor of 0.1 and a load factor increment of 0.1. And I don't provide any additional stopping conditions. I just want the solver to run the simulation until convergence fails, so until the solution diverges. And I, of course, also want to save all the results. So by doing this, I can see now, I just missed something, I think, maybe in the combination wizard. Yes, I need to click also consider imperfections. Of course, yeah, I missed that. But if I do so, all the imperfections that are that I have generated are taken into account in the automatic generation of the load combinations. So I would now have 5 different load combinations, all based on load combination 1, but with different imperfection settings, and of course all with the nonlinear geometric analysis options and the incremental eigenvalue analysis, incremental stability analysis, sorry. Now I'm pretty much set up and can run the simulation. So you will see first the imperfection cases are generated. So the buckling shapes are scaled up in a static analysis, and the geometry is applied for the load combinations here. And then for each load combination, a static analysis is performed, which I'm not very interested in, but yeah, at the moment I cannot deactivate it. But what I'm interested in and what basically is the GMNEA, that would be this structural stability analysis here for load combinations 1 to 5. And I can, during the solution phase, I can already observe the convergence behavior by looking at the convergence diagram. So for my CO1, I see that the load increment is increased bit by bit. I'm now at a load factor of 70%. And at some point it will fail. Sometimes I can already see by looking at this load factor here where my GMNEA analysis is going. So can give me crucial information whether it's it has any value to calculate further. So now we are for combination 1 at a load factor of 1.2, and now it should it should fail convergence. We see that it takes a step back to the last converged solution, which was at load factor 1.1, and now it divides the load increment into smaller steps and tries to narrow down the point of divergence. Slowly but steadily we should come there. We already also see that some of the load combinations are already finished. So load combination 2 and 3 are already finished with load factors above 1.4, and load combination 5, which was with a group of imperfection, finished with a load factor of 1.19. All right, so just quickly finish the remaining ones, and now we have all the results we need for the analysis. So we can now check the incremental stability analysis results and go through all of our load combinations that we calculated. We can either check the critical load factor down here in the table, just as Andreas did, or we can directly see it here or over here. We can on one view already see the maximum load increment that we reached, and we can check this for all the load combinations. And we can see that for load combination 1, 4 and 5, which was the group of imperfection, we have the minimum load factor. So that these would be the load cases or the load combinations which I would be most interested in analyzing. So I now want to, as an example, check the 2 design criteria I've shown you here on that slide for this load combination 5. So first of all, let's check the principal plastic membrane strain in the model. So I go to strain, equivalent, no, not equivalent plastic strain, but maximum plastic strain, and then I can just check EPL max, and if this is under 5%, and we see that the maximum plastic strain value is at 2.4 or 0.24%, it's in per mil, then we know that this is not really an issue. So the plastic, so the criterion number 2 with a limit strain shouldn't be an issue for our problem here. We can also browse through all the results, and we see that this is the case for all of the load combinations that we have checked with all the imperfection cases that we have applied. Then secondly, we should check the maximum of the load deformation curve. So I also do that inside the program. I switch the analysis type and I plot the results the other way around than Andreas. I like to have on my horizontal axis the maximum global deformation, and on the vertical axis my load factor. And yeah, I can basically do this analysis for all load combinations, but let's stick with the first one. I see that the load deformation curve has a degressive curve, so it's non-proportional, and the stiffness of this curve lowers as we reach the ultimate load factor, but we only see the ascending part of the load deformation curve. We do not see any descending part. So that's an inherent problem because we have performed this GMNEA, or we have set it up in such a way that we increase the load factor. So the solver, the standard solver, Newton-Raphson, is not able to in one step go back and decrease the load factor again. So the ascending portion of the load deformation curve cannot be derived in this under these circumstances. So for this we would need a special solver like the arc length method that could cope with that, or we would need to set the GMNAI up in a way that we increase the deformation, and then we would allow for decreasing load factors also. So that would be possibilities to also get the descending branch of the load deformation curve. But that also comes with other problems. So when I would see this, that the simulation diverged at that point, then I would ask myself, why did it diverge? So there can be different reasons. So for example, it could be because of the material nonlinearity, because of some bigger distortions of elements, could be because of some context that I have in the model, or it could also very well be that it is due to stability failure, because maybe at that point, somewhere in the model, a buckle evolves and there is a quick jump in deformations in a small area, and maybe also a decrease in the overall load resistance of the model due to this formation of the buckles. And that could also be the reason why I do not reach any further load factor, and I have divergence in my model. And that would mean that on the safe side, I can assume that when my simulation gets unstable, then my structure gets unstable. So I say, okay, on the safe side, I assume that the numerical instability is caused by structural instability, and I take the load factor that I have reached, the maximum load factor, as the maximum of the computed load deformation path. So in this case, it would be 1.18. I think this was also the maximum load factor for the other combinations. So CO2 and 3 were further up, but 4 and 5 was also 1.18. And I would use this as the decisive load factor alpha u, and I would then only need to compare this load factor with my resistance, or the product of my safety factors. And for those, I would take 1.05 as it recommended in the National Annex of EC3 Part 1.5. And for the alpha 2, I would take gamma M1, because I can clearly see that material failure is not an issue in my example. So I would adopt the value for gamma M1, and yeah, I'm German, so I would use the German National Annex, or for a project in Germany. So it would be 1.05 times 1.1, and that would give us a factor on the resistance side of 1.155. And I see that my load factor is larger than this factor, so I have 1.18 bigger than 1.155, and that would then lead to a green check. So in this case, my structure would be safe could be safely designed for buckling and all, basically all other influences as well. Okay, of course, we now have only checked the first eigenshape as mode shape affine imperfection. I can also show you how that looks like. So this is calculated in a first step before the GMNEA. So just to make sure, I would also probably have to investigate some additional mode shapes and combinations, but it's quite easy to just copy them, and the load combinations are automatically derived and can be checked. And the second thing I would also always recommend, probably if you are not familiar with this system and the structure, is to do a mesh convergency study. So I did this for the model I've shown. So the mesh size I've now actually used was 50 millimeters. And I saw that if I further decrease my element size, the results of my GMNEA stay the same. And also the linear bifurcation factors for the first mode shape stay more or less constant, so they do not change a lot. But if I increase my mesh size, so the element size, sorry, then this seriously also affects the results of the GMNEA. So I need to make sure that I use an appropriate mesh size, which I can show in such a manner like this here. All right, so that should be it. The last thing I want to show you or give you as an outlook, we are currently preparing blocks for such stiffened plates, so that will make it very easy to define stiffened plates for a GMNEA analysis, just as easy as defining the geometry and load in FE buckling. But yeah, we haven't not been able to release them just yet, but they will be added in the near future. So keep an eye up if you are interested in that. Yeah, then I would say enough being said from my side. I would hand the word over to Andreas again, so we can wrap up the webinar of today. Thank you for your attention.
Okay, thank you, Jonas, for this nice presentation. I hope we could give you a guideline for the buckling analysis of shells or plates, with this webinar. As I mentioned before, we record this webinar. You can find it on our website, or you will find it on our website in the next days. I will show you where to find all the material. Just a moment, I take over the screen. So that's the PowerPoint slide with the bibliography, with the two standards that we use today. That's the example what I presented. Also the CC handbook. Yeah, if you would like to book your free online product demonstration, for example, if you want to see any add-on or more than one add-on, and you would like to get a product demonstration, or for RFEM, RSTARP, our section and so on, then just contact our sales team via that link, or you can scan that QR code from the PowerPoint. Also, when you would like to get the non-binding offer, just contact my or our colleagues. So then I switch or turn to the website dlubal.com. Under news and events, you can find the webinars. Those are the next webinars for next week and the week after next week. So that's today's webinar. I click on it. So, and in the next days, you will get an email with a link to that page. and then you will find the recording here. You can already download the presentation slides, and yeah, you will find the models here. Just wait for the email. Okay, yeah, that should be also all from my side. Maybe a last wish: when you leave the webinar, there's a small survey. It takes you maximum 1 minute. It's quite important for our quality management. You can score the webinar. Just note that the worst score is 1 and the best score is 5. Yeah, and you can enter wishes for future webinar. Yeah, but it's not necessary. Okay, then thank you for your attention. Thanks to Jonas for his presentation. Thanks to Oliver for answering the question. Yeah, I wish all a nice rest of the day. I hope we meet each other in a future webinar. Bye-bye.